Thank you very much. Our next speaker is Anastasia Macariva, and she's going to talk about basic science to clarify the climate regulating function of the world's pristine forests. Water is the key. Thank you.
Thank you very much, and I would like to thank the organizers for inviting me to speak in this on this very interesting and important conference. And I work in the Theoretical Physics Division in Petersburg Nuclear Physics Institute, and I also represent Institute for Advanced Studies, Technical University of Munich, where I work in the research group on drought mitigation via ecosystem restoration challenges and opportunities. And I'm, as a theoretical physicist, I additionally have what can be looked at a somewhat unusual background, because I spent like more than 5 years of my life in field trips in natural ecosystems of Russia, monitoring forest ecosystems. So I would like today to share my perspective, which combines this expertise of theorists who deals with the role of ecosystems in atmospheric dynamics, and with the expertise of first-hand knowledge of how these ecosystems really work. If we look at those processes that shape what we refer to as climate change, which is the source of our concerns, so we have two related but distinct processes, and one is the change of carbon cycle. This is what we mostly refer to, and this is what we are more focused on. And you can see on this slide that currently there is a lot of emissions from fossil fuel burning, and just a little bit, like 1/10 or something, from land use change. At the same time, we also know that there has been a very radical transformation of the biosphere in the recent century, which has led us to the condition where primary vegetation was exterminated on most part of land and was replaced by agricultural systems which act very differently. And so from these two graphs, and especially from the left one, it appears that at the moment land use change is of minor concern compared to fossil fuel emissions. Likewise, we have these two processes, and we have two disturbing aspects of climate change, which is the rise of global temperature with all its negative impacts on our civilization. But at the same time, it is not a global pattern, but increasing frequency and amplitude of weather extremes like droughts, floods, and heat waves. And it is not an easy problem to answer how these two are actually related. So basic science is key to our approaching these two issues. And regarding the rise of global temperature, Professor Svante Arrhenius was the first to estimate the rise of global temperature due to CO2 change in the atmosphere. And I can tell you that it was this paper published in 1896 was really a very fine basic research combining up-to-date science. And how he calculated it, you can see that this is the graph of temperature, vertical profile of temperature, and the Earth radiative temperature, it is how much our Earth emits radiation to space, is 225, and it is approximately level located somewhat above 5 kilometers. So from here, the Earth emits effective radiation to space. So Arrhenius calculated that if we increase the CO2 concentration, So the upper radiative level will move up, and then we will have to match the incoming solar radiation. The surface temperature will have to rise. And this led him to a very accurate and still more or less up-to-date estimate that CO2 doubling results in 4 to 5 Kelvin of warming. And now, these results were not considered till 1960, but then with the development of global climate models, these models that are now run on supercomputers were built around this basic estimate of how our planetary temperature responds to CO2 increase. And these models are built originally in scientific centers, and now there are many of them, like more than several dozens. And their performance and their comparison serves to inform us about the uncertainty of our climate projections. Imagine that in each center, models are tuned to reproduce the observed record of temperature rise and some other parameters. And people use different parameterizations. So when we combine the models together, like in this coupled model in the comparison project, their mean performance, like here you can see how they reproduce the model mean, how it reproduces the mean global temperature, has several deviations from the observations. Like, for example, here you can see that sea surface temperature near South America is overestimated by more than 5 degrees. And these results in very widely different projections regarding the climate change. Here you can see several models. So this is the range of models, and this is the temperature graph, how much warming they predict. And here you can see the blue is more or less stable prediction due to radiative effects of CO2, which I referred to, which Arrhenius quantified. It turns out to be about half of what he quantified, but anyway. But these are feedbacks. This is albedo, the red one, and this means that when, for example, the ice shields melt, and there is bare land, it absorbs more sunlight, so the planet warms. And you can see that these feedbacks range widely between the models. And there are also clouds, this one. And clouds also, the cloud feedback is very uncertain and contributes about 3 degrees of uncertainty between these models. So this is how the situation stands. So all these models are realistic in the sense that they reproduce the trend of temperature and many other characteristics of the Earth system, but different ones. So now, what about the second process? When we transform native vegetation, like this is a boreal forest in Russia, and we have a lot of such forests still, and the red shows how they are being destroyed, into something different. When we deforest, when we desertify previously vegetated land, lots of things happen. First of all, the transpiration, the process is disrupted, and so the ecosystem doesn't provide water vapor to the atmosphere. And also you can see that the albedo changes. So if we compare to this, the forest is dark, so it absorbs more, and the desert absorbs less solar radiation. So how does it can be factored in to what impact it can have on climate on global temperature. Here you can see the scheme which shows how the greenhouse effect works. And if we have greenhouse gases which radiate in all directions and reflect some, re-emit some thermal radiation back to the Earth, so we can see that radiation of the Earth increases compared to the case of no greenhouse gases. Now, when we have ecosystems which transpire water vapor, this water vapor is transported by convection and passes the main level with absorbers, and it is emitted more directly to space, and in this sense we have cooling. So not all solar radiation which is converted to thermal radiation is captured by greenhouse gases, but some escapes to the upper levels from which it goes unimpeded to space. So this is the cooling effect of having transpiring ecosystems. And we can have a zero-order estimate, like at the same level of, or similar level of complexity as Arrhenius did, and from the known areas where like forests were destroyed, and knowing the power of transpiration and the magnitude of greenhouse effect, we can estimate this cooling, and it turns out of the same magnitude as from the observed CO2 accumulation in the atmosphere. So from basic estimates, we know that it is not a negligible factor. But how is it incorporated in current models? In current global climate models, they confirm this zero-order basic estimate because they show that this transpirational cooling from historical warming, from historical deforestation is around 1 Kelvin globally. But in these models, this warming from deforestation due to this destruction of the cooling mechanism is accurately offset by the change of albedo. As I showed to you, the forest was dark, then there is a desert. I'm simplifying, of course. And so in the models, these two independent effects are tuned such that they accurately cancel each other. So we cannot, and this forms this idea that actually land use change, which is ongoing. We know that the Amazon is under threat, that the boreal forests are under threat, that native forests are disappearing and are being replaced by plantations. This poses no threat because the models are built in this manner. However, if we return a few slides, looking at the uncertainty in these models, we can see that even between these models, the uncertainty in albedo change, you see these red bars, is very large. For example, this lower is a Russian model. It doesn't have any albedo feedback. And here, some other models in like Hadley Center, the albedo feedback is around 1 Kelvin. So and we know that currently all our warming is about 1 Kelvin. So how can we be sure that such an uncertain thing as albedo compensates so neatly another unknown thing, which is transpirational cooling? Besides, again, as I said, there is a huge uncertainty with clouds, up to 2 Kelvin for CO2 doubling. So, and we know that native vegetation and vegetation in generally does affect cloud formation in very profound ways. Here you can see the figure from a very famous study, which is called native cloud cover prefers native vegetation. And this is in Australia. Thank you. So, for the cloud cover, we also don't know. It is the most uncertain element of the climate system. So we don't know how it changed when we replaced native forests that have evolved to be resilient with what we have now. This is another thing. And finally, and so now most recent research shows that when we factor in the cloud cover effects that forests have, previous conclusions like those of the IPCC that forests don't matter for global temperature change because of this compensation between albedo and transpirational cooling are being radically reconsidered. So when we just begin to study these cloud cover effects of forests, and immediately we come to serious reconsideration of what we thought about this before. And another thing I briefly tell you that this cooling effect of forests is also related to atmospheric moisture transport, because you can see here, if there is convection and latent heat release somewhere up in the troposphere, this process of thermal emission to space doesn't occur immediately. It has a certain time scale, and the air must remain in the upper troposphere for a long while, and it will be then transported during this time somewhere, and then it will be able to give away heat. So, and if we look at the models, again, we can see that they don't capture the atmospheric moisture transport, and here the most important thing is the Amazon basin, which is 1/4 of global runoff and moisture transport, and it is underestimated by half. So this process of long-distance transport is underestimated in models, and this again will cause an underestimate of the cooling effect of natural ecosystems. So, what does it mean for today, or our concerns of today? We are considering exploiting forest biomass as a clean energy, renewable energy. But, I'm finishing. But is it so? If by destroying forests we do something quite opposite, we should reconsider these policies. And what I would like to propose, now there is a mainstream effort to further perfect those historical models that focus on CO2. So if somebody comes and say, oh, let us reparameterize them to show an alternative explanation, that will be very difficult because it will be against the consensus. So those actors in global change agenda, that we have a reliable estimate of uncertainties in our climate projections, I think that they should come up with the initiative of a crash test to our climate projections. We do not compare between models that already are there, but task experts with the challenge to produce an alternative model which will explain the same data from an alternative position, as I outlined, because there are all objective grounds for that, and free them from pressure from the mainstream allow them to be controversial, and see what they will able to achieve. And if they don't achieve that, and okay, we cannot produce a viable model explaining the same as CO2 model, focus models explain. Okay, it is very good result. Then we are on the right path. Don't think we are, but anyway, we will destroy native forests and replace them with plantations, and biomass will be our pillar of renewable energy. But if they do produce a viable model, this will mean that it is very, we are on a dangerous crossroad. So we shouldn't rely on the biomass, and we should preserve native, still existing native ecosystems as much as possible. So it is very important, and we are on a very important moment. Yeah, thank you.
Thank you, Anastasia. That was a really well explained, even for somebody who's not from a science background, explanation of the complexity of what you're talking about, leading to some really profound questions about reframing.